Hello everyone, welcome to Advanced Digital Synthesis. This will be the second part of Unit 1 in which we will study in detail about the MOS transistor. The outline of this presentation is we will study about the MOS capacitor in detail. We will look at the IV characteristics of NMOS and PMOS. We will look at how to encounter different capacitances in a MOS circuit. We will understand various capacitances associated with it. We will look at the two major capacitance types of capacitances, gate and diffusion. We will look at a very interesting application of MOS in terms of pass transistors. We will look at how to estimate the RC delay of a CMOS circuit. And then we'll go and see what are the non-ideal effects in MOS. The first part is obviously the ideal equations of MOS, and the latter part we'll see the various effects that make MOS deviate from this ideal behavior. So till now, in the last lecture, we saw the application of MOS as an ideal switch. That was just an introduction. So we saw how the switch behavior can be utilized to construct gates. Now the transistor in on phase will pass a finite amount of current, which will depend on the terminal voltages. What is the VDD, for example? We will see how this current depends on the voltage and on the various parameters related to the MOS. The transistor gate, source, drain all exhibit some amount of capacitance with respect to ground. Now since I is equal to C dV by dt, that means the capacitance, so we rearrange the equation to calculate the time in terms of C and I and variation with voltage. So the constant here, C and I, they actually determine the speed of the gate. What this means in other terms is that the effect of changing input, the changing input can be described by delta V here. The effect of changing input takes some finite amount of time to get translated into the output. Let's say in case of an inverter, an input rising would cause input rising from 0 to, let's say, VDD would cause the output to fall from VDD to 0. This change in effect, this change in output will depend on the capacitances of MOS and plus the current, and hence we say that it takes a finite amount of time for input to reflect on the output. We'll also see what a degraded level means. That means we say that NMOS passes a strong 0 but a weak 1. In other terms, NMOS passes a degraded level when it passes VDD. We'll see what that actually means. The symbols below are the most common. These two symbols on the left side are the common symbols used for MOS and MOS. This one, the right one with an arrow, represents the substrate connection if it needs to be explicitly shown. Similarly, the rightmost two symbols are for PMOS. So a MOS capacitor works in majorly three modes. One is the accumulation, the depletion, and the inversion. These three regions are defined by the voltage on the gate and the voltage on the drain. We'll see each of these three regions in detail. Let's go to the next slide. Okay, now let's look briefly at some of the terminal voltages. We say that we denote the voltage on gate to be VG, voltage on source to be VS, voltage on drain to be VD. For discussion's sake, let's first assume the voltage on source to be 0. Although source and drain are symmetric, they can be used interchangeably, but we assume that source is the terminal at lower voltage. That's why we say we always assume that VDS would be greater than 0, greater than or equal to 0. So in this case, let's say VGS is equal to VG minus VS. So if VS is 0, then VGS is simply VG. V gate to drain voltage is VG minus VD. V drain to source is VD minus VS or VGS minus VD. Both are true. Now NMOS, we assume for now that NMOS substrate is grounded. That means VS and the body both are at 0 voltage. For the sake of discussion, for now, we'll see how varying both VS and VB or voltage at the body will affect the operation. But for now, let's assume the source and body both to be at 0. There are three distinct regions of operation: cutoff, linear, and saturation. Let's look at each one of them. Okay, we say that NMOS is in cutoff when VGS, that is the difference of voltage between gate and source, is actually significantly less than the threshold voltage of the PN transistor. So the threshold voltage of the diode, it is very similar to the threshold voltage of a diode. Let me yeah. So the gate. So the substrate. Please note that substrate is a P-type material in case of NMOS. So the negative voltage or a voltage which is less than the threshold voltage of this junction attracts holes in the substrate towards oxide. The holes will accumulate towards the surface, or in other words, the electrons here will be pushed down. The electrons here will be pushed down. This means that there will be no current. So we say the NMOS is in cutoff region. Now what happens when we start increasing VGS and once VGS comes close to VT? Yeah, so once VGS starts approaching VT, the voltage on, or in other words, the voltage on the gate starts increasing to a positive value. It starts repelling holes in the substrate. That means now the electrons are attracted slowly towards the surface, or the holes started to go deep down the substrate. Due to this, very similar to a PN junction diode, the region which is very close to the junction is devoid of any carriers. The electric field is directed from gate to substrate. A small depletion region forms. This is very similar to the PN junction diode. I would suggest that if you want to go into the formation of depletion region into detail, please refer to the PN junction diode in your theory books. The explanation is similar. It's very same. Now let's look at. So the thing to remember here is that VGS, if it's less than or almost equal to VT, the NMOS remains in cutoff. It does not conduct any current. So as soon as VGS goes beyond VT, the electrons in application to the electric field, to the significant electric field, start accumulating towards the junction in the area here. The flow of electron is from source to drain. Now assume a small positive voltage on drain. So due to the electric field between drain and source and the electric field between gate and source, okay, the electric field between gate and source results into the electrons coming closer to the junction. The electric field between gate and source propels the electrons towards drain, resulting into a current which is called IDS, or current between drain and source. It is very similar to a linear resistor. However, in this case we are assuming that the drain voltage is small, right? We will come to that. So the definition of small here is that VDS should be less than VGS minus VT. In this case, this region is called accumulation region, where this region is called inversion region, where the why inversion, because the substrate being p-type and the carriers are electrons. That is why it is called inversion region. Now what happens? So in this region, a small increase in VDS will correspondingly result into an increase in IDS. It behaves very similar to a resistor. So it's a linear region. That's why we call it linear, because it somehow mimics the Ohm's law. Now what happens when we start increasing increasing VGS or VDS to such that the condition occurs where VDS is equal to VGS minus VT. Now when VDS approaches VGS minus VT, the region here which is very close to drain, this part, the inversion layer gets pinched off. What pinch off means is that the inversion layer shows the inversion layer could be wider, closer to source, and it will start decreasing in width as close as it goes to the drain. This is because the drain voltage, this is caused by the drain voltage, the difference in drain and gate voltage. In other words, the higher the voltage on VD, the more electrons are pulled. The region in closer to drain would start getting devoid of electrons. This causes this region to pinch off, and we call this to be the boundary of saturation. Why saturation? I'll come to that in the next slide. Why we call it saturation. So the condition to remember here is that VGS should be greater than VT. So VGS minus VT would be a positive value, and VDS would be equal to VGS minus VT, or this voltage VGS minus VT is also called VD sat. This is the voltage at which the NMOS starts going into saturation. Of course, the thing to again remember here is that VS and VB are assumed to be 0 for now. Now what happens when VDS starts increasing beyond this saturation value? So when VDS goes beyond VD sat, or which is VGS minus VT, the pinch off starts coming closer to the source. This means that the pinched off region, the channel no longer reaches drain. The condition is VDS is greater than VGS minus VT. Conduction is how a question might arise here that there is no channel here, so how does the conduction takes place? The conduction is possible by the drift mechanism of electrons. So the higher voltage as at drain pulls electrons quite fast. The electrons will travel very fast from this pinched off region to drain, but there will not be any accumulation of electrons in this area. So the conduction still takes place, but the channel current, but the current here is almost independent of the drain voltage. So even a slightly higher voltage on drain over and above the VD sat will not affect the drain current by a big amount. For let's say for now we assume that the drain current would remain constant in the saturation condition. We'll see how this is not exactly true. This is an ideal case, but yeah, it's good to start off with the ideal case to understand the functionality better. So we say that in ideal case the drain current is linearly dependent on the drain voltage whenever the NMOS is in linear region, and it saturates when VDS approaches VD sat. If VDS is increased beyond VD sat, the drain current remains constant. So combining all three regions, we can make an IV curve of this device, IV curve means that we plot the voltage versus current and see how the current is affected by the voltage. We will see the IV characteristics in one of the later slides. Now let's see. Let's try to quantify it. Let's try to quantify how the current depends on the voltage in the linear region and in the saturation region. So current depends on the charge and the time. So we answer two questions here: how much charge is in the channel, and secondly, how fast the charge is moving. Now the MOS capacitor looks like a parallel plate capacitor. The gate and the channel forming two ends of the capacitor, while the oxide forming the dielectric. So the charge in the channel. Just focus on the figure here. The Cg is nothing but the gate capacitance. So the charge in the channel, Q is equal to Cv, a very famous equation. The capacitance of a parallel plate capacitor is or Cg, the gate capacitance, is epsilon Ox, which is the oxide parameter. WL is the area, width. Just imagine it being a three-dimensional structure. The area of this rectangle is WL, and divided by the thickness of this oxide. So we define one more variable called constant called Cx, which is epsilon Ox by Tox. Now this Cox is technology dependent. What it means is that a particular foundry for this epsilon Ox depends on the type of material. So for example, for silicon dioxide, which is the most famous dielectric material in VLSI fabrication, it's a good insulator, epsilon Ox being 3.9. The oxide thickness is also technology specific. I mean, for a particular technology there will be a particular thickness, so this can be treated to be Cox can be treated as a constant for a particular technology. So the Cg is Cox WL. The voltage is at a particular point. At a particular point inside the channel, we assume that the voltage to be at the halfway point, which is so the voltage from drain to source is VDS. Since it's a linear region, we assume the voltage to be at the middle to be VDS by 2, and the voltage that matters, that pulls the charge, is that results in forming the charge, is actually the gate to this region. Since we are talking about capacitances at these 2 points, it will be VGS minus VDS by 2 minus VT. We always don't ever forget to take into account VT, because VT is the voltage that is required to overcome the threshold of the junction. So it should always be subtracted from VGS. So we got the value of C and the V. Now so the first thing we sought to define was how much charge is there, that we saw in the last slide. Q is equal to Cv. We calculated the value of C and the value of V. Now we come to the second question, is how much time it takes. The charge is carried by electrons. The carrier velocity of electrons is proportional to the electric field, the lateral electric field between source and drain. So we just go back and pause and think that what causes the charge to build up is the gate voltage. That is why in the last slide we saw that the gate voltage which is responsible for setting up of the charge is calculated in terms of VGS. Now the speed at which the gate voltage will first form the inversion channel. The drain voltage will help the electrons in conducting. So the carrier velocity will depend on the VDS. Now V is equal to mu E, where mu is the mobility of the electrons. Now the electric field is, if we go back to the basics, the electric field is V by the length through which the electric field is the voltage divided by the length of the channel. So the time for the carrier to cross channel, T is equal to L by V. time is equal to distance upon speed. This is not any special equation, very basic equation. So now we know both things. We know the value of C, we know the value of T. Now IDS is nothing but the charge divided by the time. So we plug in all the values we calculated earlier. So this the equation comes to be mu Cox W by L VGS minus VT minus VDS by 2 into VDS. You can verify this by plugging in all the things we calculated earlier into this equation. IDS is equal to Q channel by T. We define one constant which is beta mu Cox W by L. Now we discussed earlier that Cox is technology dependent. W by L are, I would not say they are technology dependent, but they are fixed for a particular. When we design, let's say, an inverter, we have to fix the value of W by L for the NMOS and for the PMOS. Here the purpose of defining beta to be constant is to study the effect of the change of voltage on IDS, assuming all these parameters mu Cox W by L are constant for the sake of drawing the IV curve. Now what happens when the transistor goes into saturation? So we see that whenever the drain, the VGD, that is or VD is greater than VGS minus VT, or whenever VDS is greater than VD sat, the channel pinches off near drain. Now as we assumed earlier, or we saw earlier in the diagram, that increase in drain voltage will no longer increase current. So now IDS in case of linear was this. So what we do is we replace VD by the value of VD sat, which is VGS minus VT, and we just rearrange the equation. So after rearranging, the result is that IDS is beta by 2 VGS minus VT square. So we see that there is a square relationship of voltage on IDS in case of saturation. Combining all three equations, the ideal MOS transistor can be represented by Shockley's first order transistor model. These equations, you can call them Shockley's first order or ideal transistor equations. Anything goes fine. The three regions being, let's recap. First, VGS, if it's less than VT, the NMOS will not conduct, the current would be 0, and the transistor is said to be in cutoff. Second case, as we start increasing VGS, but VDS is still less than VD sat, the current would be beta VGS minus VT minus VDS by 2 into VDS. So we see a dependence of IDS on VDS in linear region. When we start, when the voltage on drain goes beyond VD sat, the IDS becomes independent of VDS, and in turn only depends on the square of VGS minus VT. So this is an example of a particular NMOS device with in 0.6 micrometer process, with Tx being 100 angstrom, mu that is the mobility of electrons being 350 cm square by Vs, the Vt being 0.7 volts. If you remember the Vt of a PN junction diode, the most famous textbook value is 0.6. So if you see, the Vt is very close to that. Now we have plotted IDS versus VDS at different values of VGS. Now the W by L is used as 4 by 2 lambda. Lambda, if you go back to the first lecture, lambda is nothing but the feature size by 2. The feature size being channel length. So the here the beta is calculated and the values plugged in. So let's go through this IV characteristics. If we notice the region, the first part of the curve, it is very similar to the Ohm's law curve. That means it's a linear region where ID is increasing with increase in drain voltage, these different curves correspond to the different values of VGS. So as VGS keeps increasing, the current also keeps increasing and remains linear whenever VDI till the boundary where VDS is equal to VD sat. For a particular VGS, if we start increasing drain voltage, the current becomes constant since VGS is fixed, and in the saturation region VGS ID does not depend on VDS, so current becomes constant with increasing value of VDS. PMOS IV would be very similar to NMOS IV curve. The only difference being that voltages are and dopings are inverted. One important point to consider here is the mobility of holes. The mobility of holes is typically 2 to 3x lower than that of electrons. And this is the value 120 cm square in AMI is 0.6 nanometer process. So for a PMOS to conduct the same amount of current as an NMOS, it should be, the PMOS should be made wider. As discussed in the first class, for let's say for discussion's sake, we assume that that the mobility of electrons is twice the mobility of holes. So we would make PMOS to be twice as wide as NMOS to conduct the same amount of current. What I would recommend is that you should plot the IV characteristics, try and plot the IV characteristics of PMOS the curve and verify that the curve looks very similar to NMOS. I'm not showing the PMOS IV here. It's left as a take-home assignment for you guys. Now let's look at one very interesting. Till now, what we have discussed, VT. VT appears so much in the equations. We see that whenever VGS is less than VT, that the transistor does not conduct. So let's look at VT. VT is a very important parameter in device fabrication. It determines a lot of things. We see what VT is and how does it affect the characteristics of a transistor. So we saw that a positive VGS will result into a depletion region and ultimately into the inversion layer being formed. So VT is the voltage at which, the minimum voltage at which the MOS device begins to conduct. So what does VT depend on? Till now we have been using VT as sort of a constant in the equations, but it's not a constant. It depends on the gate material. What material is the gate made of? Usually it's polysilicon nowadays. What is the gate insulation material? The most popular is silicon dioxide. What is the gate insulator thickness? What is the voltage between source and substrate? Now till now we have been assuming the source and substrate values to be 0. We say that for calculation of the ideal IV characteristic equations, we assume the voltage at source to be 0 and the voltage at substrate to be 0 as well. VT is a function of the voltage difference between source and substrate. We'll see how does it affect in later slides. And channel doping. How VT is now for a particular technology, for a particular foundry, usually gate material, gate insulation material, and thickness would be constant. The top 3 would be constant for a particular technology, but still there will be devices on a particular chip. Some of them will exhibit high VT, some of them will exhibit average VT, and some of them will exhibit lower VT. This is not by accident. This is many times it is intentional to change the VT. How the VT is changed is by varying the doping concentration of insulator. This is the first one, is the most popular way of tweaking the VT of a particular device. It can also be changed or tweaked by using a different insulating material for the gate to increase permittivity. But this is again changing the insulating material is not easy because it will change the whole fabrication process. So that's why I say that the insulating material is technology and fabrication lab dependent. So the first one, that is by varying the doping. Concentration is the most popular way of changing the VT of a device. Now what happens when VT changes? What happens when VT increases? What happens when VT decreases? So if you remember okay, let's look at this equation VGS, which is the equation of current in saturation. When VT increases, IDS decreases. So we say that a higher VT, now a decrease in IDS would mean the device getting slower. So increase in VT will result into a slower device. A decrease in VT will result into a faster device. That is why I say that devices with all three types of VT, that is high VT, standard VT and low VT, are important for digital design, since these devices have, so the low VT will be fastest, the standard VT will be standard, the high VT will be slowest. Correspondingly, the VT also determines the power. We'll come to that later, but let me state here that a high VT, which is a slower device, would exhibit low leakage power. So for designs that are very power sensitive and not much performance is expected out of them, will use high VT devices. Similarly, low VT devices would be used for very high performance digital designs where power might not be of a big concern. So that is why all three flavors are present in today's designs. We'll see the power thing later, but just remember that increase in VT will make the device slower but less power hungry. Similarly, decrease in VT will result into faster devices, but they will consume more power. So we'll just review what factors affect the current. The factors affecting current are WL ratio, I mean how wide and how long is the channel, the threshold voltage VT, the thickness of the gate insulator TOX, which is contained in beta, the dielectric constant again contained in beta, the carrier mobility again contained in beta. So now what we have seen till now is the effect of the gate voltage, the drain voltage, or rather to be more precise, the difference between gate and source, that is VGS, the dependence of the current on VGS and VDS. Now let's see what sort of capacitances are exhibited by a MOS transistor. So in practice, any two conductors that are separated by an insulator have capacitance. They will exhibit some amount of capacitance. In case of MOS transistor, the gate to channel capacitance is very important, because this is the thing that creates the channel charge which is necessary for the operation of the MOS. However, the source and drain, they are also good conductors, that is their N+ regions. They exhibit some capacitance to the body. Why? Because they have reverse bias diodes to the body. These are called diffusion capacitances because they are associated with the diffusion regions in source and drain, and these are not desirable. Okay, let's look at the gate capacitance. Just review that. So we say that we saw that the CGS is epsilon OX WL by TOX. Now here the COX again the equation is rearranged to define a parameter called C per micron, that is capacitance per micron of the MOS transistor. That is the value is given to be typically 2 femtofarad per micrometer. This might not be very true for today's some micron devices, but yeah. So just to reiterate, the gate capacitance is very important, since this is the one that causes the charge to build up in the channel. Now diffusion capacitance, we denote two values, CSV that is the capacitance of source with respect to body, CdB, the capacitance of drain with respect to body. These two capacitances are undesirable, also called parasitic. So whenever you encounter a term parasitic in VLSI design, it means anything which is undesirable. It can be parasitic capacitance or parasitic resistance. Why undesirable? Because they make the device slower. Now the capacitance, a parallel plate capacitance depends on the area and perimeter. So the way the capacitance is decreased is by using small diffusion nodes. This capacitances are very comparable to gate capacitance for a contacted diffusion. If the diffusion is uncontacted, it decreases and also varies with process. So this figure shows three different layout techniques. In the first, the A, we see that first of all this is these are diffusion regions. The pink ones, the black ones are contacted diffusion regions. So the first one will show a lot of undesirable capacitance. In case of B, the diffusion regions are combined together and contacted. So this will show comparatively lesser parasitic capacitance compared to A, because the diffusion is made smaller, the diffusion node is made smaller. In the third case, the contact is removed from the diffusion region, and since the contact is removed, the width can also be decreased, that is the node can still be made smaller. So C will have still less parasitic capacitance. We will not go into much detail about these layout techniques. Some may be applicable to some circuits, some may not be applicable. So this is meant for a different course altogether, but this gives just an idea of that how good layout practices can decrease the capacitance, the undesirable capacitances. Right. Now this is a figure which shows all the capacitance inside a MOS. We have seen earlier that we have seen CSB and CDB, which are the junction capacitances, source to bulk and drain to bulk, these being the parasitic capacitances. Then other ones are oxide capacitances, that is the gate to channel bulk, which is this one. CGB is nothing but CG, the desired capacitance that forms a charge. Now what happens that if an ideal transistor will have no overlapping region between the diffusion and the oxide. So in a self-aligned process, in an ideal process, there will be no overlap between the diffusion, that is the two N+ regions. Let me go back to the figure. Yeah. So yeah, so in an ideal transistor, the limit at which the diffusion ends will have no overlap with the oxide layer here. So there is a zero overlap at these two, but in a practical process this is not possible. There is some amount of overlap between the diffusion and the oxide. This overlap causes two more parasitic capacitances, oxide capacitances, which are gain to drain overlap and gate to drain overlap and gate to source overlap. So we see CGD and CGS. They are also type of oxide capacitances. So we see that there are three kinds of oxide capacitances and two kinds of junction capacitances exhibited by a MOS. Out of these five, the gate to source is most desirable. The rest of them are parasitics. So the better the fabrication technique, the better the layout technique, the less will be the undesirable capacitances exhibited by a MOS. So we saw that in linear mode, let's see the value. What is the typical value of how does the value of these gate capacitance compare in linear and saturation mode. Now in linear mode, if you go back and remember that the channel spans the complete length from source to drain. It is equally, so we say that the capacitance is equally split between source and drain. So the CGS, which is the capacitance between gate and source, we say that they are equally divided, so we divide half and half from CGS and CGD. So the total channel capacitance, as we saw earlier, is CG is C of W L. This L effective is nothing but L, in this case the complete length. However, in saturation mode we see that the channel is pinched off. So actually in saturation mode the capacitance of the oxide capacitance goes lower, because the capacitance exhibited by gate to drain is 0. Why 0? Because there is no channel here. Similarly, it is approximated that CGS becomes 2 by 3 of Cox WL, and the total, therefore the total is sum of CGD and CGS, which is 2 by 3 of Cox WL. L effective is nothing but L. So we see that the gate capacitance in saturation mode is lower than the capacitance exhibited in the linear mode. Okay, now we see, now till now we have been assuming that the voltage on source is 0. The source is grounded. What if source is greater than 0? A very good example is a transistor which is trying to pass VDD. So let's see a transistor where the gate and drain are both connected to VDD. I can say this is drain or this is source, doesn't matter. The two terminals are connected to VDD, one of them being gate. Let's see what happens. Now if gate is VDD, the voltage on source, if it is greater than VDD minus VT, the VGS, that is the difference of voltage between gate and source, will be less than VT and the transistor will turn itself off. I'll repeat, if the voltage on source goes beyond VDD minus VT, the VGS will stop being greater than VT, the threshold voltage, and the transistor will enter cutoff region. This is why we say that the voltage here at the source cannot be greater than VDD minus VT, which means that if you use a pass transistor in a design and try to pass a 1 using NMOS, the NMOS will not pass VDD. It will not pass voltage higher than VDD minus VT, that is why it's called a degraded 1. Logic level 1 is represented by VDD. Since the pass transistor is able to pass only VDD minus VT, it's called a degraded 1. In other words, we say that NMOS passes a strong 0 but a weak 1. That is why in earlier circuits we saw that NMOS is used for the pull down logic, not for pull up. In most designs, NMOS is only used for a pull down network, since it passes a strong 0. Correspondingly, PMOS will pass a strong 1, but it will pass a voltage which is no lower than its threshold voltage, that is VTP. That is why PMOS is used in the pull up network, because it passes a strong 1 but a weak 0. Now what happens when we use the pass transistor circuits to form any kind of design? So let's see this this circuit using NMOS on the top. So NMOS, if its gate in one terminal is tied to VDD, the other terminal will remain VDD minus VT. Let's see a series of pass transistors. So the first one here passes VDD minus VT, but the second one passes VDD minus VT again, because it's the gate is tied to VDD, but the other terminal is not VDD actually. It is less than it is actually VDD minus VTN. So please verify using the equations of VGS being greater than VT for the NMOS to operate in the on mode, and verify that the voltage at the end of the circuit will remain VDD minus VT. There is a separate configuration here. So if you see that where we connect the output of one pass transistor to the gate of another. In the first case, the source of one transistor was connected to the drain of other. Similarly, they were connected in series. But here, the source of one transistor is connected as a gate. Now, the gate voltage should be greater than VT. I mean, the difference between the VGA should be greater than VT for a transistor to operate in an on mode. So we see that this transistor here will exhibit a 2 VT drop because the voltage on gate is decreased by VT already. Please again request you to go back to the equations and verify that this indeed is the case. So pass transistor is a very popular logic family which is used to define gates. It is not used everywhere because of this precise reason that it doesn't pass a strong one. We'll see what happens if you don't pass a strong one. What are the disadvantages? Similarly, if we use PMOS as a pull down device, we see that the voltage at source will not be 0. It will be VTP. The absolute value is used because VTP is negative. So let's say VTP is minus 0.7 volts. The voltage here would be 0.7 volts, positive 0.7. Now we saw the ideal transistor equations. We saw the Shockley model equations. Obviously, they are being ideal equations. They are not very accurate for modern transistors. They are too complicated for hand analysis. All such analysis where we want to see the voltage effect on the current and all that is usually done using SPICE. It's not using hand because these equations are not linear and they are too much complicated for using hand analysis. But for study's sake, let's devise a technique where we treat a transistor as a resistor. As we saw that in linear mode, it actually exhibits such functionality where IDS linearly varies with VDS. So what we could say is that using Ohm's law, we say that IDS is equal to VDS by R, where R is the average value across switching of the digital gate. Obviously, again, this is idealist model and it is inaccurate to predict current at a given time. But still, this model is good enough to predict the delay of a gate. Not the actual delay, but a delay value in terms of RNC, which can be compared across gates and across different layout techniques. So this is a very useful tool where you can quantify that a particular gate design, what kind of delay it will exhibit. Let's see how it is done. So we call this model the RC delay model. So what we do is we say that a MOS can be represented by an ideal switch plus a capacitance and an on resistance. Whenever the switch is off, obviously the resistance is infinite. Whenever the switch is on, there is some finite on resistance. We say that, let's say the NMOS has resistance R and the capacitance C. A PMOS will have a similar unit PMOS will have a similar capacitance C, but will have an on resistance which is twice that of NMOS because the mobility of holes is half. So unit NMOS will have resistance R, capacitance C. Unit PMOS will have resistance 2R and capacitance C. Capacitance is proportional to width. As the width increases, the capacitance increases, but resistance, if you remember, is inversely proportional to width. So the width increases, the R decreases. Now Look carefully at the figure below of the NMOS gate drain source, and K represents the width of the NMOS. Assume the length being same of all the PMOS and NMOS in the design, and assume the width to be K. K is a factor, simple factor. So now this using the RC delay model, we convert this NMOS into a switch, an ideal switch, which exhibits capacitance, drain capacitance Kc. We saw that the C is proportional to width. So if width factor is K, we say that the drain capacitance is Kc. Again, the source capacitance is Kc. The gate capacitance is Kc. Plus, there is a non-resistance R by K, since R is inversely proportional to width. Similarly, for PMOS, the capacitances remain same, but the resistance becomes double of NMOS. Now let's analyze the design and see how the delay can be estimated. These are some values of C and R for a particular technology. This is a very old technology, so yeah, you can. These are not important for modern technologies. We will just talk in terms of R and C. Now, what does a unit transistor mean? It may refer to a minimum contacted devices. The minimum contacted device will be 4 by 2 lambda, since lambda is feature size by 2. It does not matter what width, what kind of how much wide device you use for your analysis, as long as you're consistent. If all your devices in the circuit you are analyzing are consistent, then you don't need to be concerned about what is the width of the unit transistor. Let's estimate the delay of an inverter using this RC delay model. It says that estimate the delay of a fan out of one. The fan out of one means one inverter is connected to another inverter. So it's an inverter pair. Both the inverters are of same type, that is the PMOS is twice as wide as NMOS. So we convert this into an RC delay model. So since NMOS width is 1, so all the NMOS capacitances will be C. The PMOS width is 2, so all the capacitances will be 2C. The R of NMOS and PMOS would be same, because again PMOS is twice as resistive as NMOS, and since it has width of 2, so the resistance becomes R. Now this particular case assumes that so we are estimating the delay of delay at point Y. We are not estimating delay at the end of the second inverter. We are estimating delay at point Y. So how much capacitance would Y see? Y would see only the gate capacitance, because it is connected to the 2 gate terminals of this inverter. The gate capacitance, similarly, if you see Y here, it will see C at NMOS and 2C at PMOS. Similarly, we look at a case where PMOS is open and NMOS is closed. So when NMOS is closed and PMOS is open, whenever the capacitances are in parallel, they add up. So the capacitance at Y will become 2C plus C3C plus the inverter here. Since this part is open, the PMOS is open, this will go away. It will see 2C from here. It will see the C from NMOS and the R from NMOS. This C doesn't matter because it's connected within 2 grounds. So we see that in effect, whenever this transistor, the fan out of one inverter, when PMOS is open, the delay is 6 RC. That is what I said, is that using this RC delay model, we can estimate the delay of a particular design. Obviously, the delay values we are not concerned about. So let's say we are making a complex gate. There can be multiple ways of designing that gate using some logic families. Now we can estimate how much delay will that gate take. The area we would know, a gross area we will know by the transistor count, and the delay we can estimate on paper using this RC delay technique. This is useful to compare different types of circuit designs. Now what I would request is that all of you to go back and estimate the delay of few basic designs, let's say 2 input NAND gate, 2 input AND gate. We will explore this area in detail when we come to the calculation of propagation delay using logical FS. This will be very useful there. Now till now we saw that we saw the ideal equations of MOS, the Shockley first order transistor models. Now let's see what are the non-ideal effects, that is the effects we see in the real transistor. What are these effects and how do they affect this IV curve? Now this is a plot of a 180 nanometer TSMC process using the ideal model, where the value of beta, Vt and Vdd are given. This is the curve which is very similar to the curve we saw earlier. This is the ideal curve. On the next slide we would see the same process. The same process would mean same beta, Vt and Vdd values, but the model here used is not the ideal model but a SPICE model. Now please note that a SPICE model is much more complex than it is much more complex, and it mimics a real, very close to real transistor functionality after fabrication. So the SPICE models are the golden standard for analyzing the MOS circuits, both digital and analog, and these represent the actual transistor behavior on silicon. Now we see this curve and we try to notice what is different between these curves and the curve and the ideal curve we saw on this slide. This is the ideal curve and this is the actual curve of the device. What we see is less on current. So if we see the IDS here goes till 250, or let's say for VGS 1.8, the IDS lies between 200 and 250 microampere. However, on the previous slide the IDS is much higher, lies between 300 and 400. So we see less on current. We see no square law. That means the current here in saturation is increasing. It is not constant as predicted by the ideal model. Now we will see what physical effects cause this. First thing, we assume the carrier velocity which is proportional to the E field, the lateral E field, which is VDS by L, but at fields, higher fields which are present in the transistors, the fields are higher because the L is very low. In present transistors the L is of the order of nanometers. So let's say for a 40 nanometer device the L will be 40 nanometers. This is the reason why the drain voltage and the gate voltage have continued to reduce over technology shrinking, because the electric fields have been becoming so much stronger. So you can go back to your paper and see that what if the L is, let's say 180 nanometer and VDD is let's say 1.8 volt. How does that compare to L being 40 nanometer and VDD being, let's say 1 volt? You would notice that the electric field strength has been growing. That is why we have to pull VDD down. Still the electric field is high enough to saturate the carrier velocity. Why? Because what happens is that at high electric fields the carriers will scatter off atoms and velocity will reach a value which is called V-saturation. The saturated velocity Vsat is mentioned here for electrons and for holes. You see that the electrons are faster than holes. So a better model, we took V as E, mu VDS by L, but this is a better model, mu E lat E by 1 plus E lat by E sat. So the V saturation is defined to be mu into E sat. This is a curve of the carrier velocity with respect to the electric field. We see that it starts off linearly, but again it kinds of saturate at some point wherever E increases. This means that for the whenever transistor is on, in ideal model we saw that it exhibits a square relationship, but here the velocity saturated current, it increases with VDD, it doesn't increase with VDD square. So the square relationship is no more true. You can verify this by plugging in the value of V. So you will come to this equation. So we see that the velocity saturation, what it means is that the on current will not follow square relationship. It will kind of it will follow the linear relationship. But real transistors are partially velocity saturated. They do not exhibit either the first order effect or the second order effect. They follow an effect which is somewhere between 1 and 2. So we say that IDS is proportional to VDD raised to the power alpha, where alpha is a value, an empirical value between 1 and 2. This is called the alpha power model. So the Shockley model is an order 2 model. The alpha power model, so the graph here shows the simulated means the spice value, which is the most accurate. It shows alpha and the Shockley. You see that there's so much difference between the Shockley and the simulated, but alpha comes quite close to the simulated model. So the equations, these are the equations for the alpha power model for IDS, where ID sat is defined and VD sat is defined. Now another effect is called channel length modulation, which forces the transistor into the non-ideal territory. We saw that there's a depletion region, and if we increase the width of, we saw that the inversion region, the area that is filled with carriers, it pinches off if we increase the VDS. So the effective length of the channel, earlier we are assuming in linear region we saw that the complete channel is available, but in saturation region the length of the channel available is less than the full length because of the pinch drop region. So the L effective is L minus LD, where LD is the length of the depletion region, the area which is devoid of electrons. Now shorter L effective gives more current. So IDS will increase with VDS even in saturation. In ideal model we saw that IDS does not depend on VDS in saturation, but here because of the channel length modulation, the IDS will still increase in saturation mode with increasing VDS, because increasing VDS causes L effective to decrease. So this is the equation which takes care of this. Please remember, this is again just a model, just a modeling of this effect. So what here is done is that this is the equation of the transistor in saturation. Added to this, to capture the effect of VDS, increasing VDS, we've added one more factor called 1 plus lambda VDS. Lambda is channel length modulation coefficient. Please do not confuse it with the feature size lambda we have been discussing before. This is a separate lambda. It is again an empirical value which is calculated to fit the IV characteristic. So this effect 1 plus lambda VDS captures the effect of increasing VDS due to channel length modulation. There is a lot of literature available on this, so if anybody wants to look into detail, I can go through that. The purpose of this chapter is to introduce you to the non-ideal characteristics and to show you that how the ID of how the IDS varies with VDS in an actual transistor. There is one more factor called body effect. Now all along we have been saying that the substrate of the MOS is tied to 0. The body is grounded for NMOS. For PMOS obviously it will be tied to VDD. But what if the source voltage increases because source is connected to the channel? That means, what if the voltage difference? So we assume that the voltage at source and the voltage at bulk are both 0. So VBS, that is difference of voltage between body and source, is 0. What if the source is in the source at voltage is not 0 but positive? That we saw one case in terms of fast transistor. The voltage at source was not 0. So this affects the VT of the device. We saw earlier during the discussion of the VT, there was one point where it was said that the VT depends on the voltage difference between bulk and source. So this is the part where we study that. So VT is the gate voltage necessary to invert channel, but VT increases if source voltage increases because source is connected to the channel. Increase in VT with Vs is called the body effect. Now let's see how it is captured in the equation. So again we define a constant called VT0, which is nothing but the VT of the device considering VBS to be 0, plus we define a factor here which is body effect coefficient, and this body effect coefficient is so here we see the definition of the body effect coefficient. I believe that you would be studying this effect in more detail in your device physics. So this is just a recap of that. So phi s is surface potential at threshold. So see, the VSB is captured here. So if VSB is 0, VT is nothing but VT0. However, if VSB is positive, VT tends to increase. This all depends on the doping concentration and the intrinsic carrier concentration. That is why I say that if you want to revise this in detail, you should go back to your device physics book, which has much more detail about this, about the VT changing with respect to the body effect. So we saw 3 effects. We saw the body effect which changes VT. We saw the channel length modulation effect, which means what it does is that it will make IDS increase. Let's recap a bit. So we saw 3 effects which are the 3 non-ideal effects. The first non-ideal effect was the velocity saturation. The carrier velocity saturates. This means the on current is less as compared to the ideal model. Second thing we saw was the channel length modulation, which means the current increases in case of saturation with increasing VDS. Third thing we saw was the body effect, which results into an increased VT, and we discussed earlier that increased VT will mean a lower current. Now what happens, we also were all this while we were saying that a transistor that is in cutoff region will not exhibit any current, but the simulated results, if we expand that part of the graph where the transistor was in cutoff, we see there is some, even though very less, but there is some current, and the current does not go to 0 in cutoff. We see this is a very important factor in today's microelectronics. This is called the leakage current. So we see what are the sources of this leakage current. One is the sub-threshold conduction, which says that the transistor cannot abruptly turn on and off. It will take a finite amount of time to switch from on to off, and there is a conduction during that period. There is a junction leakage. That we say that the transistor is cut off because the diodes are reverse biased, but even a reverse bias diode due to the minority carrier conduction exhibits some junction leakage. Then there is a gate leakage, that is with the gate dielectrics becoming thinner and thinner as the technology progresses, there will be an effect of gate of electrons tunneling through the gate dielectric, which is called gate leakage. Now, subthreshold leakage is the biggest source in modern transistors. This is the equation for subthreshold leakage. I will not go into details of this. Again, you can refer your device physics for this. What it means, what it means is that as the technology progresses, the devices get smaller and smaller. They start exhibiting more and more leakage current. And in earlier technologies, let's say 0.6 micrometer, 0.1 micrometer, etc., the leakage current was not important. It was not even analyzed. It was not even taken into care during the design of a circuit. It was not a majority factor. But now with so small devices, all these three factors, the subthreshold conduction, the junction leakage, the gate leakage, all these three are increasing, resulting into these becoming majority factors. And we have to also think about you can there will be a transistor with, let's say, the gate is at VDD or something, or let's say the gate at 0 voltage in MOS transistor. We assume that it is off, it is not conducting current, but actually it is conducting a small amount of current. And let's say there are billions of transistors on the chip doing the same thing when the chip is off. So the billions of transistors will contribute a significant amount of current, and it is a very, very important factor now because a lot of these semiconductors are used for battery powered devices. Right. So there's one more factor called drain induced barrier lowering, which says that the drain voltage also affects VT. So we saw that the VT being affected by the difference of voltage between source and bulb. Here this effect also in this effect the drain voltage also affects VT. So VT is VT minus eta VDS. So this means that high drain voltage causes subthreshold leakage to increase. Right. So there's a note on junction leakage. Again, the junction leakage will depend on the area and perimeter of the diffusion region. We're not going into detail of this. Now we talked about gate leakage, that the carriers tunneling through the very thin oxides. As I said earlier, that it was negligible for older processes, but it is becoming critically important now since the oxides are becoming thinner and thinner. Now let's see a small note about the temperature sensitivity of these devices. So whenever temperature increases, it reduces the mobility of electrons and holes. It reduces VT. So let's try to fill in the gaps here. What happens to ion with temperature? So increasing temperature reduces mobility, reduces VT. Reduced mobility means a lower ion. So ion will decrease with temperature. If we reduce VT, so the threshold is getting reduced. Yes, it will affect the ID. ID might increase, but the mobility factor here is more dominant than the reduced VT. So ion will still decrease with temperature, but I of will increase because I of which is the leakage current depends on VT. Higher the VT, lower the leakage current. Lower the VT, higher the leakage current. Now, so what happens if the transistors are not ideal? They are still behaving as switches. They still allow us to make very complicated designs. But what do these effects matter for? They are important because of the supply. What they determine is the supply voltage choice. We'll see the logical effort in more detail. They determine the power consumption. They determine what logic families can be used. For example, can we use fast transistors or not? They matter for the temperature of operation. So whenever devices are fabricated, not all devices on a chip are identical. VSI fabrication is one of the most sophisticated and one of the most complex manufacturing techniques on this planet. What it also means is that, let's say for a particular technology, for let's say 40 nanometer, the fabrication will set the feature size to be 40 nanometer, but not all devices on that chip will exhibit a 40 nanometer channel length. Some will have 41, 42, so it will exhibit a Gaussian curve, a normal curve, where the average value will be at 40, but a lot of devices will be larger than 40, a lot of devices will be smaller than 40. This type of effect is called parameter variation. Transistors have uncertainty in parameters. For example, L effective, VT, Tox of NMOS and PMOS, they vary around typical values. I talked about channel, yeah, L effective is nothing but channel length. So a device, if it has a shorter L effective, if it has a low VT, and if it has a thin oxide, it will become faster. So in NMOS with a shorter L, a lower VT and thin oxide will become faster. You can verify it going back to the equations. A slow device would be opposite, that is an increased VT, a longer L effective and a thicker oxide. Not all parameters are independent for NMOS and PMOS. That means some parameters can be linked, that is, let's say if a process is showing an increased channel length for NMOS, it might also show increased channel length for PMOS devices. But some of the factors can be independent between PMOS and NMOS. So a graph here shows that NMOS a process can, so we use two variable notation for the device speed on a particular process. We can say that a particular part, a particular chip manufacturer can exhibit slow, which means NMOS slow, PMOS slow, can be fast slow, that means NMOS is fast and PMOS is slow. It can be fast, that means both NMOS and PMOS are exhibiting fast behavior, or it can be slow fast, that is PMOS being slow and NMOS being fast. So, but apart from NMOS and PMOS speeds, the VDD and T will also vary in time and space. We will come to this later in detail, but let's discuss this for a short time. We will see in detail why VDD and T will also vary in time and space. But let's assume for now that VDD on a chip is not. Let's say you apply a VDD on the chip pin, a VDD of 1.0 volt. The VDD will not remain. It will not. All the devices will not see the same VDD. Some will see. They will all see lower than 1 volt, but how much lower depends on the device's placement. So if VDD is with some device, let's say we compare two devices, two NMOS transistors. One NMOS is seeing, let's say, 0.95, other NMOS is seeing, let's say, 0.9. So the NMOS which is seeing 0.95, which is seeing a higher VDD, will be faster. Similarly, let's say two transistors are placed far from each other. One is seeing a higher temperature, one is seeing a lower temperature. The device that is seeing a lower temperature will be fast. So here there is a table which says what will be the fast. So let's say a typical voltage is 1.8 and typical temperature is 70. Now at let's say a device, a particular device, if it sees 0C, it will become, so a fast device, if it, for example, if the voltage is higher and the temperature is lower, the chip will be faster. If voltage is lower and a temperature is higher, the chip will be slower. So what we do is, when we call these process corners, that is, the process corners define the worst case operating conditions for a particular chip. We cannot, let's say we manufacture a chip, we give it to a customer, we have to tell him that, okay, this is the temperature range in which you can operate this chip. What if the chip is meant for space applications? The temperatures can go below 0. What if they are used in devices that are switched on all the time? Let's say mobile phone. The temperatures will go very high. They can go quite high. So we have to define a temperature range for a particular chip. We will define a voltage for a particular chip. These two are the specifications. But when verifying the chip, we will verify the chip at the worst case corners. and obviously if the chip works in all the corner cases, it should work in the middle. It should work for any combination of these corners, because these corners represent the extreme cases of the chip operating conditions. So we define four parameters. We define NMOS speed, PMOS speed, voltage and temperature. A combination of all these will define whether the corner is fast, slow or typical. Let's see this. Let's see for how does a combination of all these corners affect some of the parameters. So let's say during the design I want to the cycle time here is nothing but the frequency of operation, which means the performance of the chip. Let's say I manufacture I design a processor and I want to see the effect of all these four parameters, that is NMOS speed, PMOS speed, the voltage and the temperature, on the performance. So if NMOS becomes faster, so let's see this table. The cycle time, the performance of the chip will be worst when the devices are slow, that is NMOS and PMOS are slow. The VDD is less than the ideal, that is slow, and the temperature is again on the higher side, that is the devices become slow. So I would want to check the performance of my device at the worst case corner. The worst case corner here means all the NMOS, PMOS, VDD and temperature being on the worst case side. What about power? Power will be more whenever the devices are fast, that is they have low VT. When the VDD is higher, because power again depends on VDD, and when the temperature is on the lower side. So we say that we want to test power of the chip at a corner where all these parameters are at the F value, that is they result into a faster device. Similarly, for subthreshold leakage, I would want, the extreme case would be the NMOS and PMOS are faster, VDD is more, but the temperature is on the higher side. As we saw earlier, that a higher temperature causes more leakage. There is no need to fret a lot about this corner information if it is not clear at this point of time. This will become very clear when we look at unit 3, 4 and 5. But please remember that these process corners are, that a fabrication process is not ideal. That is there are hundreds of parameters, and most of these parameters exhibit an average value and a normal curve kind of distribution. What it means is that not all the devices on a chip will perform equivalently. That is, not all NMOS will be similar, all NMOS will be faster, or all the PMOS will be slower. Some will be slower, some will be faster. How do we incorporate this in our digital design is the thing that we will see in unit 3, 4 and 5. Now at the end of this chapter, I would want all of you to do some assignments which would be useful in making the concepts clear. I would recommend that all of you, if you are not already familiar with SPICE, use some SPICE tool, start getting familiar with it, and plot the NMOS and PMOS IV curves. One of the example of SPICE tools is LT SPICE. So LT SPICE is a freely available SPICE analysis tool from Linear Technologies. It has a lot of PMOS and NMOS models, but if you want to, so you can use that to design this, to analyze the PMOS and NMOS transistors and plot the IV curve. You could also use the ASU has something called PTM models. These are transistor models that go as low as, I guess, maybe 16 nanometer or something, which are more representative of today's technology. So what you could do is you could download the 65 nanometer models from the PTM website and try to plug in these models into a SPICE tool, so that you will be able to instantiate these transistors, which conform to the SPICE model. So please note that in SPICE, let's say a NMOS will always have 4 terminals, but its characteristics will depend on what model it's linked to. For example, it can be linked to a the model names are, let's say, BSIM something. It can be linked to a BSIM version 3, or it can be linked to a PTM 65 nanometer. So depending on what model, what SPICE model it's linked to, it will exhibit those kinds of IV curves, and you have to be very careful about the VDD. So if you are using an older technology, the VDD can go as big as 10 volts. But when we are using PTM models, please be careful that the VDD values should not exceed 1 volt. You should also so when you plot these curves, you should also note the non-ideal characteristics, whatever we discuss. That is the leakage current in the cutoff region. You will see the increasing IDS with increasing VDS and so on. So you should all verify you should all look carefully at the IV curve and verify that you are in fact observing the non-ideal characteristics. If you are not observing the non-ideal characteristics, there's definitely something wrong with the setup. So these assignments would be very useful in making the concepts clear, whatever we discuss in this chapter. Next chapter, so this was all about MOS theory. Next chapter onwards, we will start discussing about different types of digital design techniques. We'll see different logic families and so on. Thanks a lot.